Dear students, in the previous session, we have gone through the architecture as well as the simplified block diagram of advanced 80386 microprocessor. And in this video, we'll be going through the pinout diagram of 80386. So let's begin. Here is a pinout diagram of 80386 microprocessor. In this pinout diagram, you can find like there are various data lines, address lines, and control signals along with this. So let us see what are the various address lines which is available here. So here we can notice like 82 to 831. So these are the corresponding address lines. So the pin numbers that starts from 82 and ends with 831. So these are the corresponding 30 address pins. Okay. Now BE0, BE1, BE2 and BE3 corresponds to the bus enable signals. Now when it comes to the data signal, it starts from D0 to D31. Okay, so 30 address signals, 30, 31 data signals, 4 bus enable signals. So these are the major signals that is available here. Okay, major address data bus signals, that is pin numbers, that is available here. And one more thing, so 80386 is somewhat like a 132 pin IC. So representing all the pins over here will be little tedious task. So what we have done is like we have mentioned only a few pin numbers which are essential for us to understand the concepts of this 80386. Okay. Then comes to the control and status signals. So here the control and status signals include W slash R bar, that corresponds to, that indicates a read and write cycle. Whenever this W slash R bar is equal to 1, that corresponds to a read operation. That corresponds to a write operation. Whenever it is 0, it corresponds to a read operation. Then comes D slash C bar, that is data slash control. So this distinguishes a data or control signals, whether the signal is a data or control signal. Then comes M slash IO bar. So as we discussed W slash R bar, similar to that, this M slash IO bar, it selects the memory as well as the IO lines. Okay. Whenever this value is 1, it selects memory. Whenever it is 0, it will go with input output bits. Now corresponds a log signal. So what is log signal? We know that we are having bus control signals here. Okay. Whenever a data is there, whenever there is any particular data access in the bus, so what it does is like it prevents the bus access by other devices. Okay. Now the signal is coming to here, it is ADS. It is nothing but the address data string, which indicates a valid address is there on the bus. Then comes BS16. It is a bus size which indicates the bus size and also indicates this bus size is of 16 bit. If it is BS8, it indicates that the bus size is 8 bit. Next one, ready signal. So ready signal introduces a wait state to synchronize the slower memory. Next is the reset signal. So what it does is like it initializes the CPU to real mode. Next control signal is clock signal. So as you know that is the clock input of this particular 80386 processor. Then what else? So these are the major control and status signals. Okay. Then comes the DMA and coprocessor support. So that includes hold, HLDA, then peer corresponding error, then also enable. These are the different signals. Okay, where hold and HLDA, they are DMA control signals. They are used for request and acknowledge CPU hold. And coming to peer and busy, these are the signals from 80387 core processor that is used for coordinating the interrupt process. Then comes error as well as error signal, which indicates whether there is any error or system management interrupt is there. Then comes enable, which support the pipeline address operation. Okay. Then the last signal is interrupt and pin signals. Interrupt pin signals. So in this interrupt pin signals, we can see like it is INTR and NMI. So what is INTR? INTR is interrupt signal, which is a maskable interrupt request from the peripherals. And coming to the NMI, it is non-maskable interrupt that is majorly used for critical hardware family. Okay, so uh, critical hardware operations or critical hardware fault. So in such cases, we are using non-maskable interrupts. So these are the major pin diagrams, pin descriptions of 80386. As you can see in this video, these are the various control and status pins which we already discussed in the previous slide. So the various signals are lock function. So the function is like it prevents bus access by other devices. Next one, reset signal. So it initializes a CPU to real mode. Clock signal, that is the clock input. It should be of 2 into the operating frequency. So if it is BS16 or BS8, that indicates that the bus size, it selects the bus size. So it indicates either 32 bit. So if it is 32, it indicates 32 bit. If it is 16, 16 bit. Otherwise 8, then 8 bit. Then M slash IO. So it selects the memory and IO access based on which whenever it is 1, it selects memory, 0 IO access. W slash R. So whenever this is 1, it selects write, otherwise read. ADS, that is the address data store, which indicates a valid address is there on the bus. And D slash C, that is the data slash control. This distinguish data or control signals. And ready signals, which introduce the wait state to synchronize with slower memory. These are the descriptions of control and status pins. Then comes the DMA and coprocessor support signals, that is HOLD, HLDA. So as I have already mentioned, these are the DMA control signals that are used to request CPU hold and also to acknowledge the CPU hold. And this busy and that these are the signals from 80387 coprocessor that is used for coordination. And the error and SM1 hash. So this indicates whether there is any system management interrupt or error is there. And the next address NA supports the pipeline address operation. These are the different coprocessor support signals. And next comes the interrupt pins. So in this interrupt signal, so INTR, which is a maskable interrupt request from peripherals, and NMI stands for the non-maskable interrupt that is majorly used for critical hardware faults. So these are the major interrupt signals that is available in 80386 microprocessor. So next topic is like we need to understand what are the various registers of 80386 microprocessor. So we know that 8086 is having a certain registers, and in the case of 80386 we already understood like it's the extended version of 8086 and 80286. So we can say like 80386 processor has an extended 8086 register set, and all the registers of 80286 are existing in 80386 processor, and some new registers have been added in 80386. So what all registers are there in 80286, that is there in the 80386 processor itself, and some new registers are also added here. So generally 8036 microprocessor are of 32-bit and they can be used as 8-bit and 16-bit. Now we can see in detail the various registers of 80386. So these are the figure shows the various block of registers that is there in the 8036 microprocessor. So as we can see, the registers are basically divided into two types. First one general purpose register and next one is a special purpose register. So these three will together form the special purpose register. So coming to the general purpose register, the general purpose registers are 32-bit EAX, EBX, ECX, EDX. ESI, EDI, EBP, and ESP. Okay, so actually it is AX, AB, CX, DX, SI, DI, BP, and SP. So what is this AX stands for? It is nothing but accumulator. Okay, so AX stands for accumulator. So normally accumulator, it is, we know that accumulator, it is subdivided into, it is a 16-bit register, right? So this is the lower part and this is the upper part. Lower part means 0 to 8 bit. Upper part means 8 to 15 bit. Similarly, BX register, it is nothing but base register. Here also we are having lower part and upper part, lower bit and upper bit. BL is the lower 0 to 8 bit and upper is the BH. Similarly, CX is the count register. Here also the lower bit and upper higher bits are there. Now comes DX, it is nothing but the data register. Here also we are having lower bit and higher bit. Next we are having ESI. SI means source index. It is a 16-bit register. Okay. Now comes DI, that means destination index, which is also a 16-bit register. How you understood it is a 16-bit register? It starts from 0 to 15, right? Here it is 0 and here it is 15. That means it is a 16-bit register. And BP, it is the base pointer. So this is also a 16-bit register. Then SP. SP is stack pointer, which is also a 16-bit register. And you know that here it is shown as EAX everywhere and the prefix it is written as E. That means the 16-bit register can be extended to 32-bit. So that is why we are calling as extended AX, extended BX, extended CX and so on. Understood? So these are the major general purpose registers that is available for us. Now coming to accumulator case. So the major applications of accumulator register is like we can do multiplication, division, IO operations, input output operations and shift operation. Coming to B register. So the major application includes it points to the base address in the data segment. Now coming to the C register, that is the count register. As the name indicates, it can be used for counting, right? Rotates and shifts. Coming to the D register, here it indicates multiplication, division, IO, input output operation. Now when it comes to the source index, it is used for the major application is like index pointer and source string. Now coming to the destination index, it is for index pointer as well as the destination string. Coming to the base pointer, it points to base address in the stack segment. So stack segment is here only. Now comes SP, that is a stack pointer. So that is used for stack operation. So these are the overall view of a general purpose register. Now coming to the special purpose register, basically the special purpose register is of three types. First one, segment register, then comes instruction pointer, and then comes flag register. Okay, so coming to the segment register. So segment register, it is of 32-bit register, right? As you can see in the figure, it is a 32-bit register which is having a capacity of two 16-bit registers, right? So two 16-bit registers means 0 to 50, that corresponds to the uh, sorry guys, we are talking regarding segment registers, right? So segment register, this is a segment register, okay. And the segment register, it is having 0 to 15 bit. 0 to 15 bit means total 16 bit segments, which include CS, SS, DS, ES, FS and GS, right? CS corresponds to the code segment that points to the segment containing the currently executing code. SS corresponds to the stack segment. As we discussed in the discussed previously, the stack segment, it points to the segment containing the stack. Now corresponds to the DS data segments. So it points to the default data segment. So ES, FS and GS, they will provide additional segment for data access. So these are the extra segment registers. Okay. Then comes the instruction pointer. So instruction pointer, it is a 32-bit register that holds the address of next instruction to be executed. So what is instruction pointer? It has a 32-bit address like 0 to 15 is instruction pointer, and we can extend this to 32 bits. So this is extended instruction pointer. So what it does, it holds the address of next instruction to be executed. Now comes E-flag register. So this 32-bit register contains various status flags which reflects the results of address which reflects the arithmetic as well as the logic operations as well as the control bits for the processor operations. Okay, so these general as well as the special purpose registers enable 8036 processor to manage complex tasks and operate in different modes. So the theory part we have already discussed in the previous slide itself. So the register of 80386 is divided as general purpose as well as the special purpose registers. General purpose registers are 32-bit EAX, EBX, ECX, EDX, ESI, EDI, EBP and ESP. And the special purpose registers include segment registers or selector registers, we can call it like that. 32-bit instruction pointer and E flag. So the 32-bit instruction pointer, extended instruction pointer. The instruction pointer of 8086 and 286 can support program segments of 64 KB, but the extended instruction pointer register is able to support programs up to 4 GB. As we know that 80386 is having a memory capacity of 4 GB, that is why. And the code segment register, CS register, enables larger programs and its content can be changed under the program control. And one more thing is like the instruction pointer. cannot be written directly by any program. So it can be changed by the execution of certain instruction set, that is through jump, call, return, and interrupt instructions. Okay, these are the details of the registers that we already discussed. Accumulator, that is EAX, which is a 32-bit accumulator, and 16-bit means AX. 32-bit means extended AX. Then it can be further subdivided into two, right? H and AL, a high accumulator high and low accumulator. And these are its application: multiplication, dividing, input, output, and shifts. Coming to the base register, EBX, that is 16-bit register BX, and 8-bit register BH and BL, which points to the base address in the data segment. Coming to the next one, count register. So similarly, it application is counting, rotating, and shifting. Data register, which is used for multiplication, division, and IO operations. So then comes the base point, its pointer, right? Base pointer. So it points to the base address in stack segment. Then comes the source index, which is the index pointer and source string. Destination index, application is pointing to the index and destination string. Stack pointer is stack operation. Instruction pointer, that is the instruction offset, and flag, which indicates the processor status externally to show what is the status, whether it executed a particular program or something like that. So these are the various registers of 80386 microprocessor. I hope you might have understood the concept of various registers here. Thank you.